Hello, everyone, and welcome to the fourth webinar in our radiation wellness series. Just getting set up. So we'll have 6 in total this year. This will be the 5th, and we have another one next week, will be the 6th. And so it's on EMF and implanted medical devices. Why the concern? We ask that during the presentation portion that the audio and video be from the presenter only. To turn on closed captions, go to More, Language and Speech, turn on live captions. Please use the chat feature for any discussions and post questions arriving from the content in the Q&A. This will help us to find your questions for the allotted Q&A portion while allowing people to have a conversation in the chat. As the webinar is only 40 minutes in length and is immediately followed by our wellness session, time may not permit for us to answer all of them during the webinar. The answers will be posted on our website along with a link to the video recording and a copy of the slides. This can be found under Education Webinars. I will be sending a confirmation of attendance email after the webinar and will include a link to that page with the communication. I'll also include the topics covered and the length of time spent in the webinar, as some people have requested this to send to their professional association. Today, Athena Wong, radiation scientist with the Radiation Safety Institute of Canada, will speak to us about electromagnetic fields and implantable medical devices. Athena has a master's degree in physics from the University of Toronto and a Master of Teaching from the Ontario Institute of Studies and Education. At the Institute, she is a resident surveyor responsible for conducting radiation surveys, contamination surveys, and EMF surveys. The webinar will begin with Athena's presentation and be followed by a Q&A session. The final 20 minutes of today's webinar will be a movement break led by Charmaine Wong of Jiahong, Tai Chi, and Qigong in Richmond Hill, Ontario. Please note that this webinar is for information purposes only, and we will not be providing medical advice. If you have personal health concerns, please contact your primary or urgent care physician. So with that, I think Athena is here. There she is. Welcome, Athena.
Hi.
Athena's in at the office, and I'm going to turn it over, and then I'll be back online whenever it's time for the Q&A session.
All right. Thank you so much, Lynn. Yeah, thank you for the introduction. I think I'm just gonna jump into this. It seems like it's a very popular topic. Quite a few people registered for this webinar. Yeah, we have a nice attendance today. So let's see if this works. There we go. So for this webinar, I'm going to address the main issues, the two main issues of what are EMFs and what are their effects on us, right, on our human bodies. And then for the second half of the presentation, I'll be talking about implanted medical devices, like pacemakers, for example. So this is an example of a pacemaker. And how do EMFs interact with these implanted medical devices? We're going to see there will be a lot of acronyms for all of these things. So the next slide will be going over some common acronyms that will show up over and over again. But right, one thing that I want to focus on, right, are these concerns. A lot of people do have concerns about EMF and how EMF interacts with implanted medical devices. Are the concerns based on robust scientific research? And what are some of the research and also regulations and guidelines that are out there regarding EMF? Okay. So we'll be using many different short forms when talking about electromagnetic fields. So that's what EMF stands for. EMF is electromagnetic fields, right? So throughout this slide deck, I'll be using all of these to different frequency. EMF will show up a lot of times. EMI will be the second half. This is when we talk about electromagnetic interference with implanted medical devices. So that's IMD for implanted medical devices. And essentially the opposite of EMI, the opposite of electromagnetic interference is electromagnetic compatibility. So a lot of those researchers and designers of IMDs are testing their devices for EMC, right, for electromagnetic compatibility, to see if there is interference and how to shield against that interference or to reduce that through design. What else? We'll be talking about ELF, which is extremely low frequency. So sometimes you might see ELF, EMF, extremely low frequency electromagnetic fields. So this is one type of EMF that has a very low frequency. And then another type of EMF is RF EMF, or radio frequency EMF, right? And that has a much higher frequency and shorter wavelength and higher energy and everything that comes with it. ELF, extremely low frequency, is actually quite a big range of frequencies. We're going to focus specifically on power frequency EMF. So power frequency is part of extremely low frequency, and it comes from alternating current. So the electricity that we use in our homes, right, the kind of electricity that's generated in power stations is alternating current, and that is electric current that goes back and forth 60 times a second, right? So that's the frequency of, the specific frequency of extremely low frequency that we're going to focus on, right? 60 hertz frequency, and then also radio frequency. So the two types of EMFs we'll focus on are extremely low frequency at 60 hertz, and then radio frequency at a much wider range. Radio frequency is around like 10,000 hertz, right? Up to several hundreds or millions of hertz. Yeah, we're going to do our best to say the term instead of the acronym during presentation, but if you see an acronym on the slide and you're not sure what it is, you can refer back to this slide. I think people do have the ability to navigate forward and backward, and there should also be a button that says follow the presenter, right? So if you advance in the slides to see what's coming up next, there should be a button you can hit press that will bring you back to what slide I'm presenting right now. Okay, so starting off, we're going to do a little bit of physics. We're going to talk about electric fields and magnetic fields and electromagnetic fields, right? So what are these things individually, and how do they come together to give us EMF? So for electric fields, electric charges and fields are a property of the universe, right? The universe that we exist in just has things that are electrically charged, and anything that's electrically charged will be surrounded by an electric field. So electric fields surround objects that have an electric charge. Thank you, Laura. Okay. The Earth itself does have a natural electric field, as well as the human body. Molecules can be charged or can be neutral, but made up of charged objects. So if you look at something like the H2O water molecule, the hydrogen ion and the oxygen ion, those are charged, but altogether as a water molecule, that's not charged, right? So the individual components of a specific molecule might be charged. If a charged object is in an external magnetic field or in an external electric field, that's this one over here, the object will feel a push or pull from that field. Right, so electric charges inside of an electric field will experience a force. So an example of that, right, will be lightning. The atmosphere can cause a buildup of charges in clouds, which creates an electric field between the ground and the clouds. And when that field gets large enough, right, that field is going to push these electric charges that are built up in the clouds so that it travels between the cloud and the ground. So that's one type of lightning that goes from cloud to ground. There's also lightning that just stays within cloud, right? One layer of cloud has negative charges, one layer of cloud has positive charges. That creates an electric field, and when the field's large enough, that pushes those charges so that it discharges, so that it doesn't have this imbalance of charges. Another term that will show up later as well is current. So moving charges is also referred to as current, right? So in lightning itself is an example of current because it's a lot of charged particles moving through something. Here's an example of a Faraday motor. It's a very simple motor that you might have built in science class when you were younger. But essentially by connecting the electrodes of the battery with a wire, we're inducing a current in this wire, right? So in this setup, we have electricity flowing from one end of the wire to the other, and that creates a current in this wire. The way that this works, there's magnets at the bottom, and there's a current through here. So it actually connects to the next slide. And when you have current moving through a magnetic field, that's going to experience a force as well. So when you set this up properly, it's going to cause this metal wire thing to start spinning around. It's a fun little science demo. Okay, magnetic fields. Magnetic objects and fields are also a property of the universe. Some objects are naturally magnetized and have a south and north magnetic pole. These objects are surrounded by magnetic field, right? So in ancient times, like even the ancient Greeks have realized that there are things that they call lodestones. So this is a picture of a lodestone, naturally occurring lodestone, that are surrounded by a magnetic field, and they're able to attract certain type of materials, right? And it turns out they're attracted to the iron that's in some amount of soil, in some type of soil. And using these iron filings, you can kind of visualize what the magnetic field looks like, right? So here's a lodestone. It's a magnetic object. Because it's magnetized, it's surrounded by a magnetic field. The Earth itself has a naturally occurring magnetic field. This is from the core of the Earth moving in a certain way that generates this field. A main difference between us and the moon or Mars, for example, is that we have a magnetic field and Mars doesn't. So our magnetic field actually protects us from the sun. Right? This is an important aspect of this planet. If we didn't have this field, solar radiation would not be as shielded by this field, and that will cause some impact on the Earth. Okay. So just like how before, charged objects are surrounded by electric fields, if you put a charged object in an electric field, that's going to feel a push, right? Similarly, magnetized objects are surrounded by a magnetic field. If you put a magnetic object in a magnetic field, that's going to experience a force. Right, so magnetic objects inside an external field will experience a push or a pull from that field, causing them to often rotate. Typically, it ends up rotating it. Until the 1800s, so this is a bit of history of science, until the 1800s, we believed that these two properties were distinct and separate from each other. But I try to write these in a way that are parallel, right? They do have a lot of similarities. So if you compare electric magnetic fields, you have objects that kind of generate these fields, and then by placing objects within these fields, they experience a force, right? So that's the same for magnetic and electric fields. It turns out, right, one of our major discoveries in the 1800s is that these are two sides of the same coin. Electric fields and magnetic fields both come from the same phenomenon of electromagnetism. Yeah, so that was one of our significant advances made by Western science in the 1800s. By studying this relationship between electric and magnetic fields, we realized that moving charges can create magnetic fields, and that changing magnetic fields can cause charges to move. Right, yeah, the way I said it was charges, but you can also describe it in terms of fields. Changing electric fields will create a magnetic field, and changing magnetic fields will create an electric field. And when an electric or magnetic field is changing quickly back and forth, it's going to induce the other field to be generated, right? Which in turn creates more of the original field. So if we look at this diagram over here, we have the electric field going up and down. This induces a magnetic field, right? This electric field going up and down causes a magnetic field to appear going left and right, right? And then in turn, this magnetic field going left and right causes the electric field that goes up and down. So it's kind of these two components of the field supporting each other, right, and sustaining each other so that it's able to just travel in some direction. This connection between the two fields is what eventually leads us to electric motors and electricity generators, among other inventions that are used everywhere in the modern world, right? This is how we invented electromagnets, how we have power infrastructure. Essentially, this is a very important feature of the modern world. It's kind of everywhere. By understanding this phenomenon, right, of electromagnetism, how electric field and magnetic field kind of support each other, scientists eventually realized that visible light, like light from the sun, is made up of these kinds of rapidly changing electric and magnetic fields. So this is why you've probably seen this kind of a diagram before. This is often referred to as the electromagnetic spectrum. This is why all of these, right, are on the same spectrum, because all of these are made up of electric fields and magnetic fields kind of turning into each other back and forth. The main difference between the different types of the electromagnetic field is how frequently that happens, right? How that back and forth, how often that back and forth happens. Yeah, and that's shown up in frequency down here. Hertz is a unit of frequency. It just tells you how many times per second something happens, right? So for a radio wave that has a frequency of 10 to the 4 hertz, so that means that the electric and magnetic field in a radio wave will oscillate back and forth 10,000 times per second. Yeah. We're going to talk about specific types of electromagnetic field. But really, for most of this presentation, I'll be focused on radio waves and power frequency electromagnetic fields. So that's even further over here, right? That's kind of like all the way at the end over here, not really on this diagram itself. One way to think about things on this EM spectrum, you can think of them as bundles of energy composed of oscillating electric and magnetic fields. So a major part of the spectrum, right, the part that all of us are most familiar with are visible light. So these types of fields are able to interact with molecules, and they're able to excite atoms, right? They interact with rods and cones in our eyes and chlorophyll in plants. And this happens through light, right? These visible electromagnetic fields exciting electrons in our atoms. More energetic than visible light is UV light. So UV light is able to kill germs. It also does increase the chance of skin cancer and cataracts. And the way that it does that is also through electron excitations, right? So visible light and ultraviolet light are able to excite electrons that are in atoms. Even more energetic than these are X-ray and gamma ray. So because they're so energetic, they're actually able to not just excite the electrons, they're able to pull electrons away from atoms. So this is something called ionization, right? And that's why we refer X-rays and gamma rays as ionizing radiation. Ionizing radiation is classified as carcinogenic to humans, but the International Agency for Research on Cancer, IARC, we're going to see IARC a couple more times in this slide. But essentially, we've studied ionizing radiation very thoroughly, and we know it increases the risk of developing cancer, and we have a pretty good sense of how much it increases the risk, right? Especially at higher levels. Yeah, some ultraviolet, some of the more energetic ultraviolet is also ionizing and thus carcinogenic to humans. And in ionization, once again, instead of exciting the electrons, right, like in visible or low energy UV, instead of exciting electrons, it's able to eject electrons from the rest of the atom. So you can imagine that would break a molecular bond, for example, right? It kind of takes an atom, gets rid of one of these electrons, and now you have a different kind of atom. You have a charged atom. And it can interfere with molecular bonds. Okay, so that's the more energetic side, starting from visible. On the less energetic side, we have infrared light, which causes molecules to vibrate and heat up. Microwaves, which can cause polar molecules to line up with them and rotate, right? So that's also kind of a vibration in molecules. So infrared and microwaves are able to cause molecules to vibrate. So notice we're getting into larger objects. Back with gamma rays, we're affecting atoms, right? Electrons and atoms, and now we're affecting molecules. Both infrared and microwave, through those vibrations, can lead to heating effects. And then even less energetic than that are radio waves, which don't, in comparison with everything else, they don't interact with matter as significantly, but they can be absorbed on a large scale, right? They will be absorbed by buildings or mountains by inducing currents in those objects. So this is why if you're listening to AM radio and you're driving through a mountain range, that is going to block AM signal. Very intense radio waves can cause tissue heating effects, similar to microwave and infrared, not as effectively, right? You'll be adding a lot of power into these waves, and it's going to raise tissue temperature by a few degrees, versus microwave and infrared, which if you put a lot of energy, it's going to increase the temperature by a lot. Right? But we do know that radio waves can cause tissue heating effects, and they're also able to induce currents in biological tissue, right? So that's more typically a industrial hazard rather than an everyday hazard. The levels that we deal with from a Wi-Fi router, for example, would not induce any significant amount of current. But if you had an industrial machine that produces radio waves at very high energy levels, that could induce enough current in the skin that it feels warm. And we'll talk about those biological effects and those health effects on the next few slides. So just to review, right, on this spectrum going up in energy, these fields have no effect on atoms and molecules. Then we get to microwave, which causes rotations in molecules. Infrared will cause vibrations in molecules. Visible and UV will cause electron excitation in atoms. And then X-ray and gamma ray will cause ionization in atoms. Right? So as we go higher in energy, they start affecting smaller and smaller objects. I mentioned earlier that we're going to focus on radio frequency and power frequency. So here's a slide about power frequency. Power frequency is also classified as extremely low frequency. The wall outlets in homes and offices use alternating current, and that alternates back and forth at a frequency of 60 times a second, so 60 hertz. So alternating current produces EMF at a frequency of 60 hertz. So in comparison, if we go back to the previous slide, radio oscillates at 10,000 hertz, right? It goes back and forth 10,000 times per second. So AC power goes back and forth 60 times a second. Oh yeah, I've got the comparison here. It's a much lower frequency than the radio waves, and it's also known as power frequency or ELF, or extremely low frequency. Okay. Here are some properties of EMF that will be relevant. Two important properties of EMF are that they decrease with distance, and that electric field can be actually shielded fairly effectively with anything conductive. All right, the more conductive it is, the more effective it will be at shielding against electric field. Let me start with this one, decrease of distance. Because EMFs are made of energy radiating outward from a source, they follow what's called the inverse square law. Anything that is energy being sent outward from a point, right, essentially a small source, that's going to follow the inverse square law. It's kind of a geometric property of the universe rather than physics property. This means that if there is some amount of EMF is intercepting you, right? Suppose you take up the whole area of this square over here at distance r. If you count, there's 9 rays going through you as you're standing over here. Suppose you were to move further away, right? You're now twice as far. Where you're standing, now there's only 3 rays going through you. Right? And the only reason for that is because these travel in straight lines outward from a source. So if you double your distance, you quarter how much intensity reaches you, right? How much of this EMF is intercepting you. Similarly, if you go from R to 3R, if you triple your distance, the intensity of the EMF is now 1/9 as much, right? You multiply the distance by 3, you divide the intensity by 3 squared. You divide the intensity by 9. So that's why it's called inverse square law, right? As you increase one, you're dividing the other. And then if you increase by this many times, you're dividing the other by that many times squared, inverse squared. What this means is that if you move away from a source of EMF, the intensity of the fields will decrease very quickly. That's actually a very good property of EMF. That's one of the more protective things you can do. If you suspect there is elevated EMF and it is making you uncomfortable, by moving away from it, that intensity will drop off very quickly. Moving on to electric field shielding. Electric fields are very easily shielded, especially at power frequency. This picture shows what's called a Faraday cage, which is essentially chicken wire made of conductive material. So anything metallic will conduct. When the electric field reaches that conductive material, it's going to push on the electrons in that material and cause them to move in such a way as to cancel the electric field. So you may have very high fields outside of this, and then inside of the Faraday cage, it'll be a very low field. The opposite will also be true. If you have a very high field inside of the cage, this cage is going to keep that inside, right? The outside of the cage will have very low EMF in that case. Now, this is specific to electric fields. A similar thing does happen to magnetic field. To magnetic fields, but it's not as effective. For magnetic field, it's more if it's a changing magnetic field. A changing magnetic field is going to induce currents in the conductive material, and it's going to induce currents in such a way that it cancels that magnetic field somewhat. But once again, it's not very effective, and it's only for changing magnetic field. So AC magnetic field that's going back and forth at 60 times a second, there'll be some shielding from a conductive material. But if it's a static magnetic field, like from a permanent magnet, that will not be affected by this, right? It'll be affected if you're moving that permanent magnet closer and further away, or if you're moving the cage closer and further away. But aside from that, it's not going to have as big of an effect. So 2 important properties of EMF that are going to come up again. The next 2 slides are about biological effects and health effects. In previous versions, in similar presentations, we kind of went into that difference, right, between biological and health effects. Essentially, a biological effect is an effect that is measured. It's measurable, right? There's some sort of biological marker that you can measure that shows a change from some external source. Compare that with a health effect. A health effect is a biological effect that has a potential negative impact on the person. Right? So we know EMF has a number of biological effects. Not all of these biological effects are health effects. So not all of these will cause a negative impact on a human being from our current understanding of biology and health. So here are some biological effects of EMF. Human tissue is conductive. So EMFs can also induce currents in the body, right? We know that electric field will push on charged objects. There are charged objects in our bodies, right? In our atoms and in the electrons around those atoms. So if you are in an electric field, that electric field is going to push on the charged objects in your body. That can happen. We can induce currents in the body. The currents induced by power frequency EMFs are estimated to be smaller than currents produced naturally by our brains, nerve cells, and heart. So this is in typical energy levels, right? For the EMF in a typical home or office, that is going to induce small currents in your body, but those currents are smaller than the currents that naturally occur in the body. Yeah, in normal situations, right? If you're getting an electric shock, that could be a sign that that current is greater than what would exist naturally in the brain or nerve cell or the heart. To get more specific, we can say that the person standing directly under a high voltage line might get a mild shock when touching something conductive. So if you're standing under a high voltage line that is going to create an EMF, you will be in that EMF that's going to cause the charged objects in your body to move somewhat. It's going to push on those charged objects. If after that you touch something, well, not after that, if you're standing there and you touch something conductive, those electric fields may push electrons from your hand onto a different object, right? And that flow of electrons from your hand to some other object, that can give you a mild shock. Here's another relevant thing. I said earlier that electric field are shielded by anything conductive. We are somewhat conductive. We're not extremely conductive. We're not as conductive as metal or like typical rainwater, for example, right? Or lake water. We're not as conductive as that, but we are somewhat conductive. So human tissue actually does shield implanted medical devices a little bit from EMF. Okay, so here are some biological effects, right? And the mechanism for that biological effect. EMF causes charged objects in our body to move in some way. It's going to push on those charged objects in our bodies. With really intense EMF, like what you might get from an MRI, that could lead to other kinds of biological effects, more immediately obvious biological effects. Like some people do report vertigo when they're walking through a very intense magnetic field. Now, very intense magnetic fields don't come very commonly, so it's not a very commonly reported effect. But some people do say they feel like they're off balance when they're walking next to an MRI that's active. Okay, next we'll talk about some health effects of EMF. So just to recap, biological effects are things that can be measured. Health effects are things that can be measured and have a negative impact. Some of these are, I'll talk about them turn by turn. So there are some health effects from like extremely low frequency exposure, some suspected health effects from ELF exposure. So IARC, the International Agency for Research on Cancer, has classified specifically 60 hertz magnetic field as possibly carcinogenic to humans. This is because of a research paper in the 70s, in 1979, that showed a potential association between 60 hertz magnetic and childhood leukemia, right? So there was that paper that showed there may be a weak association between those two things. But here are some issues. It was a very weak association. It wasn't strong enough to say that the magnetic field was causing childhood leukemia. And part of why it was so weak is they studied a lot of people, but only a few children developed childhood leukemia. I think it was one case out of however the size of the research was. So because it was a small number of cases, there wasn't enough to say statistically for sure that magnetic field is causing the leukemia. Another concern about that paper, another criticism of that paper is that they didn't propose a mechanism. There's no known mechanism for magnetic field to lead to leukemia. So this report from 1979, it does show an association, but it's inconclusive. In fact, that same research has been repeated many times, and they still haven't come to a conclusion that 60 hertz magnetic causes childhood leukemia, right? There wasn't enough cases that it's the same issue for every time they've redone the research. The association was very weak. It's not causal. Sometimes the association isn't there. So from all of these papers, we've been looking at this for about 20 plus years. From all of those papers, it's still inconclusive. So that's why IARC has classified as possibly carcinogenic, right? In comparison, ionizing radiation, X-rays and gamma rays, those are classified as carcinogenic to humans. We know the mechanism by which those can cause cancer. And we know that it's causal, right? Ionizing radiation for sure increases the risk of developing cancer. 60 hertz magnetic radiation possibly can cause cancer in humans. So that's from extremely low frequency. IARC has also classified RF EMF, radio frequency EMF, as possibly carcinogenic to humans, right? And it's similar. We've done a lot of research on RF EMF on humans, and some of them have shown a weak association, but none of them have proven a cause, right? None of them have shown that radio frequency EMF for sure increases the risk of cancer. Similarly, there was a report in the 70s that showed possibly an increase in the risk of developing, I think it was brain cancer. But that research has been repeated many, many times, and they haven't been able to show that association, it's not made it stronger, right? It's just possibly that there is connection. Here are some other health effects from RF exposure. Here are some effects that are actually scientifically established, right? We've done these same research many, many times, and every time we've shown that there is this effect that can happen. So for radio frequency EMF, if it's below 10 megahertz, so that's 10 million times per second, right? It oscillates back and forth 10 million times per second. If it's between 3,000 hertz and 10 megahertz, you get what's called peripheral nerve stimulation. So this feels like a tingling sensation on the skin. All right. These things are moving in such a way that it's stimulating the nerves on the skin, and you can feel a tingling sensation. For radio frequency above 100,000 hertz and less than 300 billion hertz, right, 300 gigahertz, between 100 kilohertz and 300 gigahertz, you can get tissue heating effects. So once again, radio frequency can cause temperature to increase. It's not nearly as efficient as infrared or microwaves, but it does have this effect of tissue heating. So these are two scientifically established effects of radio frequency exposure. Okay. So I'm going to talk about kind of standards and limits later, but I'm going to mention something right now. Because of this possible association between 60 hertz magnetic and childhood leukemia, a lot of organizations have adopted what's called a prudent avoidance policy. Even though it's not a very strong association, they've kind of set limits on how much magnetic field is recommended. And in the city of Toronto, if you're doing a new development, the prudent avoidance policy encourages keeping 60 hertz magnetic field under 0.3 to 0.4 microteslas. I haven't gotten into Teslas yet, but that is what it is. I'm also looking at the time. We're getting close to 12:40, and I think I need to go through the rest of my slides a little bit quicker. From here on, I'm going to jump into implanted medical devices. We'll go over some standards and regulations, and I think Lynn will take over after that. I might go a few minutes over my allotted time. I'm sorry. So IMDs, implanted medical devices, more and more people have these devices in their bodies. Many of these devices are electronic and have circuitry. So because they have circuitry, both electric and magnetic field can cause interaction with those circuits. Some devices also have moving metallic components like switches that activate mechanically, right? Here are some examples of implanted medical devices. This is in Canada and sorted by volume. So I think it was 2017. There was a specific year where they did this research, and they looked at how many people got new implant medical devices in Canada. The most common was cataract lens and then knee replacement, hip replacement. So it's just ordered by volume, right? Notice on here we have pacemaker and defibrillator. So those are the ones that have a lot of circuitry. And also, if there is interference, that could cause a pretty serious effect to the person wearing them. Notice not all of these are metallic, like cataract lens is not metallic. Knee replacement and hip replacement could be metallic, but they won't have circuitry, right? So depending on the type of implanted medical device, whether they're not metallic or not, whether they have circuitry or not, that's going to affect how they respond to EMF. The most sensitive are definitely ones with circuitry. Here's an example of one of those switches. It's called a reed switch. The way that they work is there's a magnet nearby, and when the magnet activates, that closes the switch and completes the circuit. Electric field can also cause currents in an implanted medical device. Magnetic field could cause a reed switch to activate. It could also just tug on the device itself. If you have a knee replacement and you walk through a magnetic field, you may feel a pull or a push in some way. And if it's a very, very intense magnetic field, that could cause pain, right? If it's pushing it a lot, it could cause pain. EMF could interfere with sensing, with operation, with communication in an IMD. And EMF interference is also called electromagnetic interference, or EMI. Generally speaking, EMI can result in 3 possible kinds of effects. They can cause abnormal, undesired functionality. So for example, you have a pacemaker that's giving you a signal to keep your heart beating on pace. Electromagnetic interference could cause it to go faster or slower, right? Or a defibrillator, EMI could make it think that everything is fine while you're going through fibrillation. Or on the flip side, it could think you are going through fibrillation even though your heart's working fine, and cause that defibrillator to give you a shock, right? It can cause undesired functionality. It can also cause inhibited functionality. So because of EMI, it could be that a pacemaker just is not able to detect kind of how well your heart is working, and it just doesn't really do what it's supposed to do, right? It inhibits how it's supposed to work. And in very extreme cases, it could cause device failure, right? It could be that it's programmed to just shut down when there's too much interference, and then when it resets itself, it just doesn't know how to reset, right? It resets itself and it doesn't do the right thing. So all of these could happen. Sometimes these effects are benign and doesn't really cause much of an effect. A lot of these devices, when it's too much interference, they will shut down and reset, and it just resets fine. Right. So there'll be a couple seconds or a few minutes where it's not working properly, and then it goes back to working fine. But other devices, if you imagine something that's keeping your heart beating the right way, like if it fails or if it works in the wrong way, that could be life-threatening, right? So these results from electromagnetic interference could be benign or could be life-threatening. It's a wide range of possible effects. Here are some sample sources of EMF. I call them sources of EMI, but really it's sources of EMF, electromagnetic fields. All consumer electronics that use AC power will have EMF, right? Will have an electromagnetic field around it. So microwave, fridges, hair dryers, laptops, computers, anything that uses electricity will have this field around it. Some of the highest fields I measured were around electrical outlets and also surge protectors and power strips. These would often give readings of around like 300 volts per meter, right? While typical electronics might be like 30 or 40. Now, 300 is still fairly low compared to really, really powerful sources, right? Compared to industrial sources, but you can get some pretty high levels around electrical outlets and power strips. There's more and more radio frequency EMF, and that's because there's more and more wireless communication devices, a lot of those run on radio frequency around 2.4 gigahertz. So that would include cell phones, Wi-Fi, Bluetooth. If you have wireless mouse or wireless keyboard, that's going to emit at radio frequency. RFID and RFID interrogators, those are radio frequency. RFID just stands for radio frequency identification. And also anti-theft devices, right? As you're walking out of a shopping, of a store, if they have those tags, you have the detectors that detects those tags, right? So the tag is an RFID, and the anti-theft device interacts with that RFID to see if there is a tag that's walking through it. Here are just some common examples, right? As we get more and more technological as a society, there's going to be more and more of these kind of sources. For example, electric vehicles, that is a source of EMF. And electric vehicle charging stations also will produce EMF. All of these are very weak compared to what people experience in industrial settings, right? Your cell phone doesn't have that much battery in it. The amount of radio frequency EMF it can produce is less than how much electricity that cell phone uses, right? However much electricity it uses, part of that goes into producing this EMF. But the rest of it goes into just how it functions. So all of these will generate fairly low amount of radio frequency, not enough to get tissue heating effects or peripheral nerve stimulation. So next, let's talk about EMI and IMD, right? So electromagnetic interference of implanted medical devices. There's no universal guideline on this, because all of these devices they vary so much, right? And there's so many different types of electromagnetic fields that could interfere with implanted medical devices. We're going to go over some general tips and guidelines later, but there's no universal guideline. The threshold intensity can vary greatly between manufacturers. So if you look at pacemakers, different pacemakers and different units different pacemaker manufacturers and different units from the same manufacturer could have a big difference in what they're able to be compatible with. Here's a report from EPRI, so that's Electric Power Research Institute. They studied a few, I think these are implanted defibrillators, and they showed that extremely low frequency magnetic field of 0.2 to 1.2 microteslas could cause interference. And they show that for electric fields, 1500 to 2000 volts per meter for some, that will cause interference. And then others are unaffected at 20,000 volts per meter, right? So depending on the design and depending on how it's shielded and how it's built, it could have fairly low susceptibility, or it's going to work fine even in very high fields. These levels in here, in that report, they describe the levels as being comparable to field intensities under a 115 kilovolt power line. Okay. Here are some standards and guidelines for public exposure limits. There's actually no recognized Canadian standard or guideline, right? Federal or provincial. Specific organizations in Canada could have their own internal guidelines or internal standards, but there's nothing that's overarching and on the federal level or the provincial level. But there are international agencies that have guidelines. So the ICNIRP put a public exposure limit of 83 microteslas for a magnetic field and 5,000 volts per meter for electric field. So this is what they recommend in terms of how much the public should be exposed to. IEEE, the Institute of Electrical and Electronics Engineers, recommend 900 microteslas and then 5,000 volts per meter. And then the Council of European Union has put that at 100 microteslas and 5,000 volts per meter. So this for general public, right? This is not specific to people with implanted medical devices. But we can compare these numbers with people that have those devices. So if you look over here, they say you could get interference with 0.2 to to 1.2 microteslas. And here they're saying that for public, right, most members of the public will be fine in 80 microtesla magnetic field. So an implanted medical device does make you a lot more susceptible to magnetic fields. Similarly, they say that most people are going to be fine in 5,000 volts per meter, and 5,000 would interfere with some implanted medical devices, but it will not interfere with others. And once again, these fields do drop off very quickly, right? When I was measuring power outlets and surge protectors, I had to put the meter right against it, like touching it, to get those readings of, I think I was getting 300 volts per meter. If I moved it away even 10 centimeters, like if I move it away a few centimeters, it drops down to like 20 very, very quickly. Same with the magnetic field. I think the highest I was getting was maybe 13 microteslas, and that's with it right next to it, right? If I move it a few centimeters away, it drops down to like 0.1, 0.7. Like it drops down very quickly as I move the meter away from the sources. Health Canada Safety Code 6. So Health Canada, right? Let me go back to over here. There's no recognized standards for power frequency magnetic fields, but there are standards for radio frequency EMF, right? Health Canada has a Safety Code 6 that sets limits to radio frequency EMF exposure. So these limits are set to prevent those two biological effects, those two health effects. These limits are set to prevent peripheral nerve stimulation, which can happen in this frequency range, and tissue heating effects, which can happen in this frequency range. The Safety Code 6, it actually gives you a bunch of equations. So I had to pick some frequencies to run through those equations to try and calculate that. So Safety Code 6 says if you're around sources of radio frequency exposure, if you're around a 2.4 gigahertz source, right? So that's cell phones, Blu-ray, wireless mouse and keyboard, wireless headsets. You'll want the electric field to be under 45 volts per meter, a magnetic field to be under 0.14 microteslas, or a power density of 5.3 watts per meter squared. If it's a higher frequency, so 5G Wi-Fi is going to use a higher frequency of radio frequency EMF. These limits go up a little bit, right? It's just because of how it depends on frequency. To give you context with this power frequency, we're asked to evaluate some smart meters. We didn't have it with us, so we can't really do measurements, but the manuals say they emit radio frequency at 1 watt, right? So the meter itself emits at 1 watt. So to get a power density of 5 watts per meter squared, I mean, it's not really, I guess you have to be like just around it. Like if you're completely surrounding this source, that may increase that 1 watt to 5 watts per meter squared. But if you're standing, a few centimeters away from this source, that's going to give you something that's much smaller than 1 watt per meter squared. Yeah, like these values are hard for people to measure, right? But you can look at the wattage of your device, and some of that wattage will get turned into radio frequency EMF. And through that, you can kind of interpret it like, how powerful is it, right? If it is generating EMF, how powerful could it be by looking at the wattage of it? There are Canadian medical standards. So Health Canada maintains a list of recognized standards for medical devices. There are at least 6 of these standards that are related to EMF, and one in particular for the test protocols of implanted medical devices. So there are some standards for manufacturers to test their devices before they are allowed to put it onto the market. Right? So these implanted medical devices are tested, but there is still, there's definitely a lot of knowledge gap, right? You can only do that test when it's not inside of a person, because when it's inside of a person, you're doing testing on a human being, and that's a lot more different, right, than doing a test on just a device itself. But there are Canadian standards regarding testing of those devices before they get implanted. So what are some general guidelines regarding EMI of implanted medical devices? Please read the manual. Right. Oftentimes the manual will say what the tolerance range is, what it's able to withstand. Please talk to your doctor and employer. Both of them should know that you're in a situation where you may be exposed to elevated EMF and you have an implanted medical device. Ideally, they're able to work with each other and the manufacturer to figure out what is safe, what is possible to work with, and also the distance to source. If there is a very powerful source of EMF, the further you are away from that, the weaker it is going to be, right? So even if you just take a few steps away, that's going to decrease that intensity very quickly. And then the other thing is to observe hazard symbols. So these are ISO hazard symbols, international standard hazard symbols. This one is no pacemakers, no metal implants, right? No metallic implants. Typically, these are around MRIs and other elevated EMF. These are warning signs. This just says there is a source of non-ionizing radiation, and this says that there is a magnetic field here, right? So you'll probably see these paired together pretty often. But these are some typical hazard symbols regarding electromagnetic fields and potential electromagnetic interference. Now I'm looking at the time. I think I've left very few minutes for questions.
All right.
Sorry.
Yeah. No, we appreciate it, Athena. Athena's very passionate about this. And when we're looking for webinar topics that Athena offered, that this was something that she had been researching and would like to share with the public. So I hope that people do not mind. I don't see a lot of questions had come in, but we did have a number of questions that came in through the registration, and that Laura, Athena, and I had worked to get those answers created, that we will put that document together as a Q&A document and post it on the website. We also had Charmaine Wong here to do some Tai Chi, but we've eaten into the Tai Chi time. So Charmaine, that we will get you on our webinar next week. We do appreciate that you're here and ready to go. That this is a topic that is of interest to people. We felt it was important, so that's why I didn't wish to cut Athena off. So Charmaine, I see you there. Thanks,
okay.
Charmaine.
Sorry.
Yeah,
No
so
problem.
we'll get Charmaine next week. And again, if you do have questions, we'll stay on the chat. There's about 3 minutes left. If you did have a question that you had been planning on asking, if you want to type it out now, that we would find the answer and put that in the Q&A document. Just one of the questions that, if we don't mind, as the last 3 minutes are here, that because our focus tends to be here about precautions and safety, that just a note that if you do have an implanted medical device and you're in a workplace that is known to have strong magnetic fields or electromagnetic fields, that there needs to be some sort of a plan put in place for doing some measurements. That typically what you would want to do is take a look at what your medical provider, as Athena had said, you talk to them about what the limitations of the device are, what types of things are concerning. The employer needs to look at what some of the risks are, right? What fields are there, and if the employer doesn't know that there might be a need for a survey. Athena's gone in and done surveys at workplaces looking at EMF fields for various workplaces. But sometimes you can find that out from the manufacturer of the device, that type of thing. And then what you'd want to do is look at the controls, right? What type of controls do you have? And it's in workplaces that have this occupational health and safety mindset, you don't want to just leave it up to the worker then. It's like, oh, it's there, stay away from it. That's not a good health and safety practice. What you want to do is you have responsibilities under health and safety laws regarding provision of a safe workplace, as well as training employees on the hazards in the workplace. So employers should be involved in the determination of the risks of EMF to employees with implanted medical devices. And the resulting required safety controls. If the source of the fields cannot be removed or shielded, then barriers, warning signs, training, administrative controls, etc., that they should be implemented, just like any other hazard in the workplace. So that was one that I just kind of wanted to go through. Sorry to Athena to cut off our Q&A session. But just remember that it can be a hazard in the workplace. And then when you're looking at your risk, right? Like what are the risks involved and what are the controls that need to be in place? So with that, it's 1 o'clock. Everybody's, for those of you in Eastern time, your lunch hour is probably over, and it's a lovely Friday afternoon. For those not in Eastern time, we're glad that you're able to make it through your workday or your evening, depending where in the world you are. We get people from all over. So thank you again, Athena. Thank you to Charmaine, to Laura, and to Kim here from the Institute from being here to support the webinar. So, and thanks again to all of you that continue to support us. And we'll see you next time. That we do have one next week on the 27th, where I'll be going through the different regulations around ionizing radiation in Canada. So we'll see you then.